Let's do our solutions for assignment 2.9. First, we're going to review the definition of a limit. Remember that in calculus, when we're interested in a limit of a function at a value a on the x-axis, we don't actually care what the value is exactly at a. We're interested in what happens as we get close to a on either side. Do we reach the same limit as the two little calculus men are walking from either side of the highway? So our definition requires that L would have to be a real number to be a limit. And then we need to check if the limit as x approaches a from the left side of f of x is equal to L, and the limit as x approaches a from the right side of f of x is also equal to L, then our conclusion is the overall limit as x approaches a of f of x is equal to L. So there could be a left-hand limit and a right-hand limit, but it's only an overall limit if both sides agree. For continuity, our brief way of thinking of continuity was, could we sketch the graph without picking up our pen? But to write that more mathematically as a definition, we could actually ask three questions. So we could say f is continuous at some place x equals a if first f is defined at that value, so if it's outside the domain, then clearly it's not continuous. Our second question is, does the limit exist? So does the limit as x approaches a exist? And that would still allow for a hole in the graph or a pop point. So the third thing we have to test is the actual definition. So here's where we actually get to the important part of the question. Is the limit as x approaches a of f of x exactly the same as you would get by direct substitution? Is it the same as the y coordinate when you put a into the function? So you're checking to make sure that there's no pop point. So question 3 says, which of the above definition it will actually define continuity? And the third part is enough. Why would we bother with parts 1 and 2 then? Well, if 1 and 2 aren't true, then we don't even have to bother to ask the question about part 3. But part 3 is actually the definition of continuity. So part 3 alone is sufficient. Question 4. Again, it looks like we have a vertical asymptote. We want to make sure that you are out of the habit of just looking at the denominator now, so you won't be surprised when you have a removable discontinuity. So this graph has a hole in the graph at x equals 2. But we could plug the hole. We know that the y coordinate, the hole is actually at a y coordinate of 4. So that would help us. You could make this graph, but you don't have to make the graph anymore. It's almost the same as the line x is equal to 2, or x plus 2, sorry. But it has a hole in the graph at 2, 4. So we've seen this several times already. So the limit as x approaches 2 from the left-hand side, we're looking on the left-hand side, we get very close to the y coordinate of 4. And the limit as x approaches 2 from the right-hand side, we get very close to a y coordinate of 4. So since the two limits left and right agree, we say there's an overall limit. F of 2 does not exist. So is f continuous at 2? So notice, even though there is a limit, there is no continuity. And of course, we know that if you've already graphed it. So remember that if I asked what type of discontinuity, this is a removable discontinuity. So remember your vocabulary as well. All right, let's take a look at 5. This piecewise defined function, the first part of the domain is everywhere except positive 2, and we've certainly now got the idea why we reviewed all these common functions. We know, I don't want to write that in the way of the other point. This is at 2, 1. We're going to keep seeing these same functions repeatedly. So there's the first part of our domain. And the second part of our domain is when x is exactly equal to 2, then our y-coordinate is equal to x. F of x is the same as y. Y is equal to x when x is 2. So we've got the point 2, 2 as a pop point. So now let's answer our questions carefully. The limit as x approaches 2 from the left side, we're looking right here on our graph. The y-coordinate gets as close as we want to -1. As x approaches 2 from the right-hand side, so we're looking right here on our graph, and the y-coordinate approaches as close as we want to 1. The limit as x approaches 2 overall does not exist. F of 2, however, does exist. F of 2 is defined to be 2. So is it continuous at 2? No, and this one we would say has a jump discontinuity. And again, notice that here, even though part 1 would be satisfied, part 1 of our definition, is the function defined at 2? Yes, it is. But part 2 right away, does the limit exist? No, it does not. So we don't even have to think about part 3 of our definition of discontinuity. All right, in number 6, we've got another piecewise defined function. When x is less than 2, we've got our basic parabola slid up 1 unit. So going over to 2, this would have a y-coordinate of 5. When x is exactly equal to 2, our y-coordinate is 5. So notice that that happens to plug the hole here. So at 2, 5, now the second part of the graph plugged the hole that was open. And our third part of our function, when x is greater than 2, we have a line with a y-intercept of -1 and a slope of 3. So rise 3 units, run 1 unit. Sorry, let me get that out of there. Rise 3, run 1, and it picks up right here, and it would be a line with a slope of 3. And by coincidence of how the function is defined, it continues from the place where we left off. So let's check. We think that we should have continuity here. So our limit as we approach 2 from the left side, we're looking at this position. We get very close to 5. Our limit as x approaches 2 from the right side would be 5. So our overall limit is 5. And f of 2 is also equal to 5. So yes, this satisfies all 3 parts of the definition. The function is defined, the limit does exist, and not only does the limit exist at 5, but f of 2 is exactly equal to that limit of 5. So all 3 parts of the definition are satisfied. All right, one more. Absolute value. So if in doubt here, we know where the turning point of an absolute value graph is what x value would produce 0. So here we have an absolute value graph that is a straight line. That's another way of thinking about it here. It would be a straight line 3x minus 2. So a slope of 3, but the negative part of that line is going to flip to be positive. So I think I should draw this whole thing dotted maybe. So if this were the line, let me talk about this a little bit more here. So what I'm saying here is this is the line 3x minus 2. I better think about that first. So the absolute value of this function would take anything that was negative and flip it up to be positive. So when x is equal to 2, plug it in here to be careful about the y coordinate. So we would get the point 2, 4. So here we have an open circle. Doesn't look open. So we've got 2, 4, and now I'm going to make this graph solid. And I can erase this. You didn't need to graph that line, but that might be a helpful way to think about that if you weren't sure about absolute value. All right, and our second part of the domain, when x is 2, we get a point at 5. And the third part of our function, when x is greater than 2, we've got the square root of 2x plus 3. So let's substitute 2 in here and we'll get square root of 4 is 2. So we have the point 2, 5. So this square root graph is going to be something like this, and it happens to pick up from the point 2, 5. So if you can graph the function clearly, you already can see that the graph is not continuous at 2. We know that this has a jump discontinuity. You didn't have to graph it, though. You could have answered the questions just by plugging into the algebra. So the limit as x approaches 2 from the negative side is 4. The limit as x approaches 2 from the positive side is 5. So our overall limit does not exist. So that's part 2 of our function, or part 2 of our continuity test. Does f of 2 exist? Yes, it does. It happens to be 5. So we know we don't have continuity here because the overall limit does not exist. All right. Let's get some more practice with limits. I promised you were going to see more of these. When you see question 8, we're doing a left end behavior and a right end behavior with a square root. So I hope this sounds familiar from a previous assignment. So we talked about the fact that this is approximately the same as when x goes to negative infinity. This negative 8 we can think of as negligible. The square root of x to the 6th is not x cubed. It is the absolute value of x cubed. So as x goes to negative infinity, this limit, think of negative numbers, this will be negative 1 rather than positive 1. And we have the same idea here, but as x goes to positive infinity, can you see that it's going to go to positive 1? You guys have seen this graph already. That's our same graph. Positive 1, negative 1. We've seen this several times. So it's not going to be a cubic function. In question 9, when we have a binomial with a radical, we use the trick of rationalizing by the conjugate. And do not distribute in the denominator. In the numerator, you can see we'll have x plus 10 minus 16. X plus 10, sorry. And in the denominator, let's leave these as separate factors. I hope you can already see that we've got a common factor here. This numerator is actually x minus 6. So the numerator is going to cancel with that term. And now we can solve our 0 over 0 problem. Remember, if we had put 6 in the original statement, we would have had 0 over 0. But now we can plug the hole. So if we put 6 in for the leftovers here, our numerator is 1. And putting 6 in for x, we've got square root of 16 plus 4. So we'll come up with a limit of 1/8. The limit as x goes to infinity, this is one of our common functions, e to the negative x. Remember that e to the negative x is the same as 1 over e to the x. So we know that this is going to be a horizontal reflection when the negative is in front of the x term. As x goes to infinity, we've got our horizontal asymptote here at y equals 0. And a transformation of the natural log graph. So if we graphed the natural log function, any logarithm, we know this is our basic logarithm, so now we've got this 2 units to the right, so our asymptote and our graph, so our key point is now at 3, 1, and our asymptote is at x equals 2. So we want the limit as x approaches 2 from the positive side. So we can say that this goes to negative infinity. Notice that's not an actual real number limit, but we know that it's headed towards negative infinity. And now we're doing the same graph in number 12. The limit as x approaches 2 from the left side. There is no such limit because it's not even in the domain of our function, so it does not exist. Well, here we've got something new. Let's think what happens as x becomes very large or very small when we have an exponential function. As let's do part B first. As x goes to infinity, think what happens if you did even a number as large as 1,000, and clearly it could get much bigger than that. 5 to the 1,000th power is such an incredibly huge number that adding 7 or subtracting 2 would become negligible. So as x gets very large, we can ignore these two terms, and we can see that the value of our fraction is going to be very close to, not -1 here, +1. So here both the numerator and the negative and the denominator will be positive numbers, so they'll cancel out to give us 1, something divided by itself, in other words. So what happens, what's the difference if x goes to negative infinity? Something very different. Now think what we're talking about here. So for example, we are thinking of 5 to the negative 1,000 power over 5 to the negative 1,000 power. So this is 1 over 5 to the 1,000th. So now this is a very tiny fraction. So now these two terms become negligible. So something very different happens as we go to negative infinity. So 5 to a negative power becomes a very small fraction, closer and closer to 0. So what's left, our limit goes to -7/2. So that would be an interesting function to look at the graph. Again, it has two different horizontal asymptotes.